Okay, let's get started. Does anybody have any questions? Yeah.
Midterm date, it says on the syllabus is tentative. Is it?
Oh, it's not tentative anymore. Yes, that's right. It's on that day. It'll be on that day in class here. So you should be well on your way in thinking about what projects you're going to work on. In particular, thinking about teams. What are the possible topics? Okay. Hopefully you're making some progress figuring out what you want to do there. Okay. So today we're going to leap ahead in the book to chapter 10. We're going to the next batch of material is going to focus on concurrency issues. We've already seen a good bit about concurrency issues, both through the modeling side when we talk about composition of state machines, and in the design side when we talk about interrupts and I/O mechanisms. So today we're going to focus. We're going to pop up one level to the operating system and microkernel level. And the reason for doing this in this order is that you're going to be working, probably many of you in your projects, with the VxWorks system on the PowerPC if you use the Compact Rio for your project. So it's a good idea to get a handle on what the issues are. And moreover, the issues in dealing with concurrency and multitasking and issues like that in embedded systems are kind of a big deal. It's the easiest way to mess up the design of an embedded system, and it's also extremely tricky and very difficult to get your head around. So what we're going to focus on in class is what the principles are in multitasking. So we'll start with multitasking today, and then we'll progress to looking at scheduling issues. So how do you regain control of multitasking? So there's an image in the book that I think is kind of useful to put these things into context, which is concurrency comes from the Latin word running together. Okay, and it just means there's a bunch of things going on at once. We're all used to it in the physical world. It happens to us all the time. We're constantly dealing with it, reasoning about it. Whenever you are thinking about what's going on around you, whenever you're driving a car, whatever, you're actually reasoning about concurrent processes. And yet, for some reason, when it comes to software, reasoning about concurrent processes becomes impossibly difficult. In fact, it's very puzzling, really. Software systems will behave in inexplicable ways due to concurrency issues. And the principal reason for this is that the core abstractions in software are sequential. They're algorithmic. The term algorithms comes from an ancient Arabic concept, and it refers to step-by-step operations. Okay, you start with some initial state, you transform that state to get a new state, you then transform that state to get a new state, you then transform that state to get a new state, and you go through this sequence of steps until you draw some conclusion. That's what an algorithm is all about. And we've built software around that principle of sequential operations. And many people, if you've sort of been brought up as a software person, you think, that's perfectly natural, and concurrency is the weird thing. But it's actually exactly the opposite. Concurrency is perfectly natural, and the sequential steps are the weird thing. The sequential steps are the things that have been drummed into your heads in our process that we call education since you were in kindergarten, right? They're not natural. They're actually rather difficult to learn, the sequential steps. They're very useful, of course, okay? But natural is concurrency. That's what the physical world does. Stuff is happening all at once. It's not happening as a sequence of steps. Okay? And yet, there's this tremendous mismatch then. The abstractions that we use in software have a very difficult time of talking about something that is extremely natural in the physical world. And because we try to retrofit software with mechanisms that overlay on top of these sequential steps a notion of concurrency, that retrofit turns out to be extremely difficult to reason about. And we're going to talk about this issue today and why you really sort of have to sort of step back and think about holistically how the system is behaving in order to understand concurrent processes in embedded systems. Okay, so in software, how does concurrency arise? Well, this picture shows three different layers. The one layer we've already talked about. At the processor layer, concurrency arises through this mechanism that we call interrupts. So an interrupt says, okay, you're proceeding happily through this sequence of steps. You're doing something algorithmic, and then all of a sudden the external world wants attention. So it raises an interrupt service request line, which is either pulling a pin of your microprocessor high or low, and your microprocessor responds by suspending what it was doing and going off and dealing with this other thing and running another bunch of sequential code, and then eventually coming back to resume where it left off. Okay, that's the processor level where concurrency appears at its most primitive. It also appears in pipelining in processors. In fact, modern processors today use rather sophisticated pipelining techniques that can even do things such as execute instructions in the opposite order from which they're presented to it. It has to analyze the dependencies across instructions and so on to ensure that it maintains this illusion of sequential execution, because the software abstractions are about sequential execution, and so any correct execution of the software has to behave as if it executed sequentially, right? At the processor level, concurrency also arises when you have parallelism. So if you have a multi-core machine, this particular somewhat old Apple has a dual-core processor in it, and as a consequence, there can be two threads executing genuinely simultaneously in time. That leads to some really interesting interactions because these two threads are capable of accessing, reading and writing the same memory contents. All right, and as a consequence, you completely lose this illusion of sequential execution because you can have two threads that are stomping all over each other's data in very unpredictable and difficult to control ways. Okay. So that's the ways that concurrency arises in software at the processor level. One level up from that, we use what we call operating systems. And by the way, I want to point out to you that this notion of an operating system is not something that is a law of nature. Okay, this is an invention of humans developed in the 1960s, and virtually, the concept is unchanged since the 1960s, which is remarkable given that the technology has changed so much. But the basic concept of what is the role of an operating system in software was defined a long time ago and has been kind of frozen in time. In my opinion, it's time to rethink it. But nonetheless, we're kind of stuck with it for the moment. So what does an operating system do? Well, an operating system builds on these mechanisms to create this illusion of sequential execution and being able to do multiple sequential executions at once. Okay, so one of the things that an operating system will do is handle your I/O mechanisms so that you don't directly have to deal with interrupt service routines that are triggered when your Ethernet PHY chip requests an interrupt because a packet has just arrived over the Ethernet link, or your wireless the wireless modem in the hardware requests an interrupt because it's got a packet to present to you. So the question is, what do you do with that? Well, if you're working at the processor level, a piece of hardware pulls the voltage on a pin on the chip high or low. And at the hardware level, all that does is cause the current, whatever's currently executing to stop executing, and a new program to start executing at a certain location. What should that program do? Well, if you have an operating system, the code that executes at that point is operating system code. It figures out which device has just requested an interrupt. If it's one of the network devices, it goes and reads memory mapped registers to read those packets into memory, okay? And then it deals with those packets in whatever way the operating system has set up to deal with those packets. When you're writing embedded systems, you often have to work at that low level where you're writing the code to respond to those interrupts. Even when you're not working at that level, if you have an operating system and there are those kinds of activities going on, you have to be aware of how they work because they can affect the behavior of your system, okay? So that's one of the interesting things about working with embedded systems is that you can't just work at this pure software abstraction. It's not effective to do that with embedded systems. You have to understand what the hardware is doing with that software. Okay, so at the multitasking level, that's where concepts such as processes, threads, and message passing appear. Threads are not a native concept in processors, okay? They're a fabrication of an operating system. Similarly, processes are not a native concept in processors. They're a fabrication of the operating system. One level up from that, you can start to think, instead of thinking about processes, threads, and message passing, think instead about concurrent models of computation. So concurrent models of computation are, for example, LabVIEW, where you've got a bunch of tasks, a bunch of blocks that in your head, you might as well think of them as operating simultaneously. Whether they're operating simultaneously or not, you don't care, actually. What you do care about is what is the model of interaction. The model of interaction in LabVIEW happens to be data flow, which means that a downstream block will perform its operation only when it's got data to perform it on. And once it has operated on some input data, it will not operate on that same input data again. It consumes the input data, operates on it, produces output data, and sends it on to a downstream component. Okay? That's a data flow model of computation. That gets overlaid on top of a multitasking operating system if you're running on a multitasking operating system. So if, for example, in the lab or in projects you use LabVIEW embedded, you can take LabVIEW programs, run them on VxWorks on the PowerPC on the single board Rio, and LabVIEW takes care of the interface between your model of computation, creating this data flow semantics on top of VxWorks, which is operating at this middle layer, which is handling the multitasking operating system. Okay? LabVIEW can also skip layers here and take at least certain block diagrams and synthesize them directly onto an FPGA, which is a layer below this in the hardware. Okay? These layers show what's happening in the software only. At the hardware level, concurrency is kind of everywhere, right? Hardware is intrinsically concurrent. Okay, so what we're going to do, we've talked a bit about this layer. We're going to talk now about this middle layer, okay, the multitasking layer. So first of all, we need to define threads. So threads are sequential procedures that share memory. And a key concept in threads is that you can think of them as logically executing simultaneously, but they actually interleave in some way. Okay? So if you have a suite of sequentially executing steps, conceptually, they should behave as if those steps are interleaved in one grand sequence. That illusion is relatively easy to create on a single processor with a single thread of control. Okay? In fact, if there's a single processor, it's only ever executing one step at a time anyway, and so you do genuinely get this interleaving semantics. The operations in each thread interleave in some way. If you're executing on a multi-core, however, it's a little more problematic, right? And in fact, it can be very difficult to maintain the illusion of threads actually executing in an interleaved fashion. Okay, but I'm going to defer any detailed discussion of that issue for now. We're going to assume for the moment that threads are going to execute with their steps being strictly interleaved. So at the core, there's going to be a sequence of steps that are taken. The steps may be one step from this thread, then a step from that thread, then another step from that thread, then another one from that one, then that thread gets suspended and we go back and do a step from this one, a step from that one, and so on. Okay? But let's assume for the moment that they actually genuinely interleave. That's called an interleaving semantics, by the way. All right, so if you have threads, what are the uses for this? Well, one of them is, of course, to react to external events. In fact, you can think of an interrupt service routine as being a thread that interleaves in some way with some executing process. It tends to, there's an asymmetry there that threads don't share at the operating system level, right? So interrupt service routines don't get suspended to resume execution of a thread, typically. But interrupt service routines can be suspended to process another interrupt. And interrupts often have priorities, so there'll be a well-defined order in which these preemptions can occur. Okay? But there's an asymmetry there that threads don't share. At the operating system level, any thread can preempt any other thread at any time. Now, threads can have priorities, just like interrupts can have priorities. But what do you think it means for a thread to have priorities? What happens in the Java virtual machine, you can set the priority of threads when you create a Java thread. What does it mean? Yeah.
Maybe they get more fraction of the CPU time.
They get
They get a larger fraction of the CPU time.
They get a larger fraction of the CPU time. That seems intuitive. Other ideas? Yeah.
Maybe if you have like two threads that need to access the same memory location and one always gets.
You have two threads that have to access, are trying to access the same memory location. One will have, well, it's a little hard to see how, so, yeah, you can use priorities for that. It's tricky to use priorities for that. It's actually rather difficult to enforce an order of memory accesses using priorities alone. We'll actually look at a pretty clever technique that is used in Simulink, actually, to use priorities to enforce the order in which accesses to memory occur in a multitasking system. But you'll see that it's not actually that easy to do, but it is possible. So in Java, setting the priority of the thread actually means nothing. In fact, the Java specification, the language specification says an implementer of a Java virtual machine is free to ignore the priority. Okay? It has no semantic meaning at all in the language. Nothing. Zero. So why is it there? Well, I guess when they defined the language, they thought it might be useful someday, and someone might pay attention to it at some point. And you might create a Java virtual machine that actually paid attention to the priorities and used them in some way. And people have created Java virtual machines that actually pay attention to priorities. They haven't really been widely used, and the mechanism by which they pay attention to priorities matters. So if you have if you have a program that's relying for correct behavior on the priorities that it sets for its threads, it could run correctly on one virtual machine that does pay attention to priorities and run incorrectly on another virtual machine that also pays attention to priorities. Okay? There's no assurance, and in fact, in the language definition, it says, don't worry about it. Priorities don't really matter anyway. So it can be really tricky to understand what these things mean. Unfortunately, a lot of embedded system designers who haven't taken a class like this, they'll sort of hack a system together, and gee, it doesn't work. So then they up the priority of some thread that keeps missing deadlines, and they just tweak priorities until it seems to work on the bench. It's an extremely unsafe way to do design, right? They don't really ultimately know why it works when they get it working, and they don't know that it'll continue to work, and they don't know under what circumstances it'll fail to work, okay? And yet, sadly, that's often the way it's done. So working with priorities on threads is a really tricky thing. We're going to look at this in some detail. So you can also use threads. So there's a notion related to interrupts called an exception, which is typically triggered by software, okay, where, for example, if something disastrous happens, so in Unix systems, for example, and actually most modern operating systems have memory protection. So if you're running a program that inadvertently or perhaps maliciously attempts to address a region of memory that the operating system does not want you to address, such as, for example, the interrupt vector table, which if you could address it with an application program, you could really wreak havoc, right? The operating system sets up the hardware to trap those instructions that access those locations, okay? And so what happens when that address appears on the bus, an interrupt occurs, and a service routine defined by the operating system takes over, and typically will abort your program and issue a message that is in traditional Unix systems called a segmentation fault. How many of you have seen a segmentation fault message? Yeah, it's pretty common, right? I mean, it happens, for example, if you dereference a null pointer. Why would dereferencing a null pointer be a problem? Why is memory address 0 bad? Remember the memory maps that we looked at? Well, memory address 0 is often the top of the interrupt service table, right? Or it's the address of the program that you start executing when you reset the machine. Okay, so if you can write into that address, you can then reset the machine and start executing arbitrary code. So you generally don't want user programs accessing those memory locations. All right. So there's many mechanisms. There's actually several layers of abstraction in there. There's also virtual memory that sort of translates the user address space into physical addresses. These things all interfere with your ability to understand what the hardware is doing. Okay, but the key thing that we want to get across is that the way the hardware works is actually ultimately at its root pretty simple. Okay? The program is running sequentially, reading and writing memory addresses, and when things are happening concurrently, it may be an illusion. It may be just that they're actually happening sequentially, and things are getting stalled and suspended temporarily. Okay, so that's the third bullet here says that another use of concurrency is creating the illusion of simultaneously running different programs, even when you're not actually able to simultaneously run different programs. A fourth reason is to exploit parallelism in hardware. If I run a multi-threaded Java program on this machine, if it's a well-written program that actually is able to run both threads at the same time, it'll typically run twice as fast as on a single core machine, because the two cores can execute simultaneously. But whether it runs twice as fast depends on a lot of factors. Someone want to tell me what those might be? If I have, yeah. Yeah, so there might be interlocking mechanisms that will stall a thread. But there's even more insidious errors. I could have two threads that are accessing completely disjoint regions of memory. Okay? They're not communicating at all. And I run them on a multi-core machine, and they may not run twice as fast. In fact, they might even run slower than they would run on a single core machine. How could that come about? Non-communicating threads accessing disjoint regions of memory. You have an idea?
They share a cache.
They share a cache. So they could be stomping on the cache, right? So one of them gets a chance to execute, pulls a bunch of stuff, spills into cache, spills out the cache, okay? And then gets suspended by the operating system. And then the other thread starts running and says, oh gosh, none of the stuff I need is in cache. Let me, all of its stuff will get dragged into cache, spilling the other thread's stuff from cache, okay? The two programs could end up running slower on a dual core machine than on a single core machine because of interactions through the cache. These things become very difficult to understand, of course. And if you care about the timing of programs, this can be deadly, right? So dealing with real-time constraints is another primary reason for doing concurrency, right? If you don't care about timing, you don't need concurrency to run programs, right? I mean, that's the way programs used to work. When I started programming, way back when the dinosaurs roamed the earth, you would, punch a bunch of cards at a punch card machine, create a stack, that was your program, and stick it in a window, and then you would get complete control of the machine for a fraction of a second, during which time the machine would run your program, get a segmentation fault, and then print out the entire contents of memory in hex, and you'd come back to your window, and there would be a stack of paper this thick showing the contents of memory when the segmentation fault occurred. Not a very gratifying experience, but a sadly very common one. But at that time, computers didn't care about timing except as a performance issue. So in fact, even today, most people who talk about timing in computing are really talking about performance. Faster is better, simply because if it takes too long to do a computation, you get tired of waiting, right? But in embedded systems, we have a rather different situation, right? Which is that we actually care when things happen. And it becomes important to do things at the right time. So a good example of mine is, suppose you're designing the software to control an internal combustion engine, like the one in your car. One of your primary tasks is to tell the spark plugs when to fire, okay? If faster is always better, then it would always be better to tell them to fire earlier, right? If your program finishes sooner, go ahead, tell them to fire, keep moving. But it doesn't work that way, right? You have to tell them to fire at the right time, okay? And in order to do that, you may need to heavily exploit concurrency. So for example, you've done your computation, you've figured out when the spark plugs should fire, but it's not that time yet. What should you do? Well, one option would be to just do a busy wait in the processor and not do anything else until that time comes. But you might have other stuff to do, some diagnostic routines to run or something like that. So doing that busy wait would be kind of silly. So what you might do instead is write to some memory mapped registers to set up an interrupt service routine to reawaken this particular thread at the appropriate time to fire the spark plugs, okay? Go run your diagnostic routines. When the interrupt occurs, at that time, you're close to the right time to fire the spark plugs, write to the memory mapped register that causes the spark plug to fire, and then you're done, right? So that's a concurrent style of programming with the goal of getting things to occur at the right time. Yeah, question. What's your name again? Chris. That's an extremely good question, and the problem is that it's very dependent on the system that you're running on, and it can be very hard to tell what the jitter is going to be. So if you're running on bare iron with no operating system, you can usually get pretty good control, and you can get the jitter down to on the order of microseconds or even sub-microseconds. If you're running an operating system, however, one of the problems that is with an operating system is that it will often be doing stuff during which it disables interrupts. And how long does it keep interrupts disabled? Well, kind of depends on what the operating system is doing, which piece of code is running, and non-real-time operating systems don't really necessarily, the designers don't even necessarily pay much attention to that issue of how long you keep interrupts disabled. In a real-time operating system, a well-designed real-time operating system, they will often tell you that the operating system will never disable interrupts for more than 1 microsecond.